Imagine yourself at a carnival. All the sights and sounds, the smells of the delicious foods. You standing 2, maybe 3 feet away from others in line, waiting for the fabulous Ferris wheel. I'm going to stop that music because it's actually kind of annoying, but if that didn't get you ready for this, I don't know what will. We are going to start talking about sine and cosine functions. And so I want to take notes here together. I want us to look at this before you go to the Khan Academy that I've assigned. Hopefully the Khan Academy will give you some more practice, fill in some gaps, but then we'll come back for a check-in a little bit later. So you might want to get a calculator. If you don't have one nearby, you might even want to try to do this before listening to this video, because I think a lot of this you are capable of doing with the right triangle trig knowledge that you have already. But we are going to get into graphs of sine and cosine, why they look like they do, and that kind of thing here. So this might be a little bit of a long video, so please feel free to pause when you need to go back if you need to, or maybe even just to come back later if you can't finish it all at one time. All right, well, let's just get started. Imagine a Ferris wheel that has a radius of 20 feet. Its center is 25 feet off the ground, and it completes 1 revolution counterclockwise every 30 seconds. Now, we all know that a Ferris wheel is boarded at the very bottom, obviously, but for our purposes, for the unit circle that we're going to talk about later, we are going to assume for the rest of this time and every other time we talk about a Ferris wheel, we are going to actually assume that we board this thing at the rightmost position. Okay, so let's draw a picture of this Ferris wheel. Get some of the details down on this paper. The radius, of course, you can draw this anywhere from the center, but the radius is going to be 20 feet. Let's see, it says that the center, so we'll say, let's maybe make the ground here and say from the center to the ground is 25 feet. And then, of course, an important piece of information is that it completes 1 rotation or revolution every 30 seconds. So that's going to come into play to help us figure out all these questions that we have here. So another word for that, the fact that it rotates every 30 seconds, that's known as the period of the function, or the period of the Ferris wheel at this point. The period is how long it takes to go through 1 cycle. So to go around the Ferris wheel 1 time takes 30 seconds. That is known as the period, and we'll talk more about that later. And you'll hear more about that in the Khan Academy videos as well. All right, so question number 1. After 1 second on the ride, how high would a passenger be? So again, we are pretending that the passenger starts right here. So the passenger starts 25 feet above the ground, based on our information here. So the question is, 1 second in, how high will they be? Well, if it takes 30 seconds to go, we'll say 360 degrees 1 time around, then I don't think it's too much of a stretch to realize that every 1 second that goes by, you go 12 degrees. Now, please understand this is not a linear situation. This looks nothing like a line. I cannot say that I'm going to go up the same height every second. This is not going to be a consistent linear thing. So we can, though, say as we travel around, we could say that in 1 second's time I will go 12 degrees. We can say that is true. All right, so what do we do here to find this out? How do I find the height right here? So that is from here to here, here to the ground. What is this height if I've traveled 12 degrees? Well, you might have noticed that what I kind of drew here looks like a right triangle. So I'm going to draw that right triangle down here just so we can mess with it a little bit. Here's the right triangle that I just drew. We know that this is 12 degrees. We know, of course, that the radius is consistently 20 around. And since I drew this from a point straight down to the ground, I know that this is a right angle as well. So if I can find this height right here, that would be this height right here, and all of course I would have to do is add 25 to that to get the total height at that moment. And I think we all know how to do this. I think we could figure out how to find this h here. I could say that the sine of 12 degrees is of course opposite over hypotenuse. In order to get h by itself, of course, I would just multiply both sides by 20. And so this, put it in a calculator, would tell me this height here. And then of course, I'm going to add to that the 25 that is from the ground to the center where I started. So I'm not going to do all the calculations. Like I'm not going to punch them in the calculator as we do this video, but again, you might want to pause and do that yourself and then check with me. When all is said and done here, you should get 29.16 feet. And that should make pretty good sense. I mean, you started at 25. You didn't go too long. You didn't go too far. You went about 4 feet higher. So a total height of 29.16. Okay, let's move on. After 2 seconds, well, 2 seconds later, I would have traveled, of course, 24 degrees. So I can draw a very similar triangle here with the 24 degrees. And now I could say that the sine of 24 degrees is going to be h over 20. So my height would be, of course, 20 sine 24 plus that extra 25 that I started with. And here you should get 33.13 feet. Again, interesting to note kind of like what has happened there and all of that. Makes sense, 33.13. Okay, great. After 3 seconds, how high would the passenger be? Well, some of you are probably noticing that you don't need to draw this triangle every time. You kind of see a pattern, and that is what I hope that you are starting to see. It looks to me like I started with 12 degrees, I went to 24 degrees for the next second. So it looks like I will probably have a sine of 36 degrees for this next one. So if you're starting to see that, you might also notice this pattern, 20 sine blah, blah, blah plus 25, 20 sine blah, blah, blah plus 25. So this one would be, of course, 20 sine 36 degrees plus the extra 25. And so if I put that in my calculator, I should get 36.76 feet. That's how high I would be at 3 seconds. When would the passenger be at the highest point? So when is the passenger going to be up top here? Well, if it took 30 seconds to go all the way around, it's going to take 15 seconds to go halfway around. So it's going to take half of that, which would be 7.5 seconds to get to the very top. What would happen after they reach the highest point? Well, you've been on a Ferris wheel, or you've at least seen them. Once you reach this highest point, of course, you're going to start going back down. So your values are actually not going to get any higher. They're going to actually go down and actually repeat. If you think about that on a Ferris wheel, you go from 25 feet all the way up here to your highest point. And we can think about what that highest point would be. If this is 25 and this is 20, straight up, the radius is 20, the highest you'd ever reach is 45 feet. And then you would start coming back down. But if you are here, well, that's the same height as when you were over here. You're just repeating those heights. So, yeah, to answer the question, the heights would start going back down. And repeat. Okay. After 12 seconds on the ride, how high would the passenger be? Well, there's a couple of different ways you could think about answering this question. For those of you who see the pattern and realize that all you were doing is taking the seconds and multiplying by 12 to get the degree that you've traveled around, well, then you might go straight to saying that's just the 20 times the sine of 12 times 12, which is 144 degrees, plus 25. You might jump right to that. If you don't jump right to that, you can think about a circle. You can think about this circle up here, and you can think, well, if that was 7.5 seconds up top, and that's 15 seconds, then I'm going to be somewhere in here. And you could think about where you might be at 12 seconds. You will know that that's got to be an obtuse angle. It's going to be all the way over here. You've gone certainly more than 90 degrees, but less than 180 degrees halfway through the circle. And so you could think about 12 seconds as being the same. Look at this for a second. You could think of 12 seconds as being kind of the same as 3 seconds away from 0. 12 is 3 seconds away from 15. So those are obviously going to be at the same heights. And if you plug that into a calculator, make sure you're in degrees, you plug that into a calculator, you will actually see that you do get the exact same answer that we got at 3 seconds. And that should make good sense to you because we are repeating those values. Those are at the same height. So think about that. That's a really big connection to make, that those values are going to repeat. Okay, so let's talk about further along then. 18 seconds into the ride. So I'm going to draw this over again since I turned the page, but 18 seconds into the ride, I'm going to actually be down here. This is 15 seconds. I'm actually 3 seconds away again, but I'm now underneath. If this is what we knew to be 25, I'm actually going to be at a height less than 25 now. So see what happens when you use your pattern. If I use my pattern and I think of the height still as 20 sine of, if I do 12 times 18, that's 216, plus that 25, you will notice that I actually get, if I type that into my calculator, I would get 13.24. Let me double check that real quick. Yeah, 13.24 feet. So I'm underneath here, less than 25. Okay, checks out. What is interesting to note about this is I could figure this out in a different way if I had simply gone back. Let me just switch this page for a minute. If I had thought over here at 3 seconds what this value was before I added 25, if I just type that into my calculator, I get 11.75. And so if this was 11.75 and then I added that center height, well then I should really just be thinking, if that's 11.75, then that's also going to be 11.75 because those are the same distances, those same angles away. That angle and that angle, they're the same angle. And so what I could also do is say 25 minus that 11.75, and you'll see that you actually get this 13.2425-ish number. So it's so many beautiful connections with this, so much symmetry, and that is a very important thing to see. All right, after 33 seconds on the ride, how high would the passenger be? Well, 33 seconds, of course, means they've already gone around once and they're going back. So if I hit the same place I started at 30 seconds, well then 3 seconds later, I'm, of course, going to be the same as I was at 3 seconds because it's the same place. So that's going to repeat, and it'll keep repeating over and over and over again. Can you generalize your work to write an equation? Well, I think we've kind of already done that, but if not, let's formalize it here. The height of a rider seems to always be found by saying 20 sine of 12 times the time. And remember this, I'll talk about that in just a second. 12 times the time plus that extra 25. And I want to talk to you about this. This 12 degrees is what's known as the angular speed. Now, don't get all caught up in that right now. You'll talk more about that in pre-cal, but angular speed just means how many degrees are they going every second? They're going 12 degrees every second, so it would make sense then that I would take that 12 degrees per second and add or multiply it to seconds to get the total degree that is being traveled over time. So that's why that number is what it is. That's what it's telling us. Okay, so let's try to graph this, and I want to talk about the features of the graph that you will see. Looking at our equation, just words that you will see on Khan Academy and that you will hear me talk about again as well. In our equation here, this 20 is what is known as the amplitude. Amplitude, you've probably heard that word before, up or down. It is how far up above the middle you go and how far below the middle you go. So it makes perfect sense with this Ferris wheel. You go 20 feet above it, above the center, and you go 20 feet below the center, and you keep repeating that over and over and over again. So that is what's known as the amplitude, and when we graph this situation in a minute, you will see that on the graph as well. Let's see, this 12, as I've already told you, this 12 here is what's known as the angular speed, but what is more important about that is that it tells us the period. Remember, we talked about the period a minute ago. So when we are graphing something, it's often very important to be able to find the period from a graph or to be able to use the period to graph. If we take the entire 360 degrees and we divide by the angular speed, we actually get the period. This is what's known as the period. This is the time it takes, and we were given this already. This is the time that it takes to go through one whole cycle. Now what we did before is we actually took 360 degrees and we divided by the period and we got the angular speed. So these obviously work together. The biggest thing I see people doing incorrectly is telling me that that's the period. That is not the period. This number right here in front of your variable is not going to be the period. It is going to be the angular speed that can tell you the period. And it tells you pretty simply. You take 360, divide by that, you get the period. So please keep that in mind and be aware of that when you're watching the Khan Academy videos. And then lastly, this 25 is simply known as the vertical shift, which you have lots of experience with. Vertical displacement, vertical shift. It's just telling you where the center of the graph is. Where's that midline that you were traveling about? All right, so let's graph this and let's see all of these features in the graph that we have. At time, this is time, of course, and this is height, of course. And so I don't need to know how to graph a sine graph in order to make this graph because I have information and I know that this is cyclic and I know that this is going to keep repeating over and over again. And I know that at time 0, I am 25 feet off the ground because I'm starting at that midline. I know that. Great. I am not going to go through and plot a whole bunch of points here. I'm going to plot the important points. We sometimes call these the five important values or whatever that you could plot. This is how I always graph a sine graph and how you will begin to do it this year, but really more so next year in pre-cal. Graph these graphs. If I start at 25, I also know that I end at 25. If I go one cycle around, I'm going to end at that same spot. So I know that it takes me 30 seconds and I'm going to be right back here. So I always plot the beginning and I plot the end. That's how I graph sine graphs. In the middle of time, 15 seconds into this ride, I am also at that same midline. I'm at the middle of the Ferris wheel. Here's where I start, here's where I end. Halfway through, I'm at that same height. So I am going to, at 15 seconds, go ahead and plot that point as well. There's 3 of them right there. All right, that first trip around, between 0 and 15 seconds, I have already said that halfway through, at 7.5 seconds, I'm at my highest point. So I'm going to go to 7.5 on here. And at my highest point, I've already said that I am at 25 plus 20, which is 45. So I'm going to go on my graph to 45, and I'm going to plot a point. That's the highest I'm going to get. My lowest point, we haven't really talked about that, but I think you can figure that out. My lowest point is going to take place between 15 and 30. And it is going to be 25 minus that radius, which is 20. So the lowest the Ferris wheel ever gets is 5 feet off the ground. So let's find that point. And let's mark it. You should see some beautiful symmetry here. And now I'm just really going to connect these. And what I want to tell you about the way we connect, that we are making a sine curve, and you've probably seen sine curves before. This is one cycle. Please note that this Ferris wheel keeps going. This Ferris wheel could continue. This is going to repeat over and over and over again. Let's go on forever. Even though it doesn't make sense in the context of this problem, I could continue a sine curve in this direction as well. Of course, forever and ever. I'm going to keep doing the same thing over and over again. Please make sure that you connect with smooth curves. Like I said before, this is not linear. This is not a linear situation from here to here. This is a curved situation. From 1 second to the next, it is not the exact same increase in height. I cannot say things like, for every second I go up X feet. I can't say that. It's not a line. Within this graph, note these special properties that we talked about before. The amplitude you can clearly see from here to here, that is 20 feet. Also from here to here, I can see the amplitude, 20 feet. I am going up 20 and going down 20. You can clearly see the midline right here. This is the middle of my graph. I oscillate above and below this perfectly, symmetrically, beautifully. It's going to keep repeating that. Look at this symmetry that is happening here. And I'm always going about this midline, this vertical shift, this displacement. And of course, I can't see the angular speed on here. That's expected. I can't see that by looking at the graph, but what I can see by looking at the graph is the period. So I can see that from the beginning of this to the end of this is 30 seconds. That is how I'm going to identify the period of any graph. I look to see how long it takes for one cycle to go. And that's how I know the period. Okay, great. So please, if you need to look at that again, pause that, whatever, please do, because this is a lot of information at one time. Number 11, let's also take another look at a circle. In which quadrants are the values of sine positive and where are they negative? So if I'm just looking at a typical circle on a coordinate plane, let's say that's the origin there. If I'm talking about height, or if I'm talking about the y value as being the sine, then the sine values are going to be positive here and here, because that's when I'm going up. And of course they're going to be negative here and here, because that's when they're going down. And I see that reflected in this Ferris wheel, not so much with positives and negatives, because I'm not going underground in this particular Ferris wheel, but I do see that my height is larger than the middle here, and it's smaller than the midline here. So I can get that idea of positives and negatives and where those are in the quadrants as well. Your calculator knows this, of course. If you plug in an angle that's greater than 180, it's going to give you a negative value for your sine. You can practice that if you want. Try plugging in the sine of 200 degrees. It'll give you a negative because it knows it's way over here and it'll be a negative value. All right, we think of positive angles as being formed from the positive x-axis and moving counterclockwise. So if I'm ever talking about an angle in trigonometry, I'm going to think about it as being formed starting right here. This is my initial side. And if that's a positive angle, then I'm traveling around in this direction, counterclockwise. That's how I form my angles. If I'm talking about a negative angle, I actually go backwards, but you don't need to think about that right now. You can wait until pre-cal to talk about that. So if we think of positive angles as being formed from the positive x-axis and moving counterclockwise, where are my angles positive and negative? So very similar question in number 11, but now I'm just going to use particular angles. So a sine is going to be positive from 0 degrees to down here, where of course this is 180 degrees. Now, what are the sine values at 0 and 180? Well, they're 0. So I'm going to not include them as being positive. Where are these values negative? Well, we're going to pick up at 180. And all down here, all the way back to 360, you're going to have your negative values. Again, your calculator recognizes that. You should recognize that. That's how sine is going to work for us. Okay, so that is just kind of a brief overview of how a graph of sine would work and all the bits and pieces there. The last thing I want to do is to talk about cosine a little bit. So let's see how that would differ. We're going to go through this a lot quicker because it is my hope that you would pause the video now and try to think about cosine by yourself first, and then come and kind of check this. We're going to take the same Ferris wheel. We're going to consider the horizontal displacement of a passenger. Now, this is a little weirder, a bit of a stretch, but we're going to do it. So we have this same Ferris wheel that we've talked about before, but now we're starting here, but we're thinking about horizontally where the passenger is. So they start over here as far right as they can be, and we're going to call that, since the radius is 20, we're going to call this positive 20. They travel around and they get over here to what we're going to call the most left that they can be, which we're going to call negative 20. Now obviously they can't be negative 20 feet, we get that, but just for our purposes here, we're just going to think about their horizontal displacement as being positive 20 over here, negative 20 over here, and everything in between here. So of course, up top, highest point, they are going to have a horizontal displacement of 0. They're going to be right at the center. Okay, so you can take a minute, you can find various placements for the rider along this ride. If I go back to the very first triangle that I drew here, and I know that this is 20, and I know that that's 12 because we're thinking this is 1 second in, just like we did a few minutes ago. Instead of looking for the height here, I'm looking for this value. I'm looking for the horizontal displacement. If I was to draw that same triangle over here, it would look like this. I'm looking for how far over they are. So, you might notice I'm not going to use sine here. I'm going to use cosine because I have adjacent and I have hypotenuse. So I'm going to say the cosine of 12 degrees is x over 20. So then my x value, of course, would just be 20 cosine 12 degrees. Now note, I don't have to add anything off to the end of this time because I don't have to put in that extra height here. So I'm not talking about height anymore, I'm talking about horizontal displacement. So I'm actually good to go with that value, which is around 19.56 feet. Again, makes sense, it should be less than 20, it should still be positive, and so on. Take a few minutes, find a few more, but I think some of you are probably ready to go ahead and write this equation because you kind of see what's going to happen over and over again. If I am looking for my horizontal displacement, I'll call it P. I'm going to simply say 20 times the cosine of 12 times t with nothing added off to the side here. This is going to be able to tell me at each second what my horizontal displacement will be. Now notice, at some point I got to go negative. These are all negative values here in this second quadrant. My calculator knows that as well. If I was to type in the cosine of, let's say 10, we'll put a 10 in here for 10 seconds because we know at 10 seconds we're somewhere in here. So the cosine of 120 is going to be negative. And my calculator is going to tell me that, and I'm going to multiply that by 20, and I'm going to get my negative value for my horizontal place at that point. Okay, so graph this equation. Let's graph this equation then and see what comes of it. Again, I have the same ideas as I had for sine. That is still the amplitude. That's still going to be that thing that tells me the period. Period is the same as it was a minute ago though. So for this one, I'm going to draw my own graph. I actually need the bottom here. I need these two negative values to happen here. So this is still going to be time, and this is going to be the horizontal place. I'll just say placement. At time 0, I am actually as far as I can be. So I'm actually at my highest point, which is 20 at time 0. So notice with the sine graph, I actually started here on the axis. Now I'm not. I'm starting at my highest point. 30 seconds in, I'm just going to kind of sketch this. 30 seconds in, I'm right back there at that largest value. So notice it's going to be a little different looking graph. Halfway through my ride, 15 seconds in, I'm actually at my most negative value. So I'm actually down here at negative 20 when I graph. Started at my highest, went to my lowest, go back to my highest. In between these times, 7.5 seconds, we're actually at 0. We're actually at the very top of the graph, which would have a horizontal placement of 0. So as you might imagine, halfway through here, 3/4 of the way through, but halfway through the bottom, I'm actually also going to be at 0. So you notice if you connect these, you get a very similar looking curve. And notice that if I was to continue this, I would have what looks like a sine curve just shifted over a little bit. You'll talk more about that too in pre-calc, but for a cosine graph, for our purposes, we're going to think the difference between a sine and a cosine is that the sine graph, as we saw a moment ago, starts at the midline, does its thing, comes back to the midline. Cosine graph actually is going to start at its maximum, does its thing, and comes back to its maximum. So that's how we're going to see the difference between those right now. But once you do get to pre-cal, you will notice that I could take this graph right here and write it as a sine graph that has been shifted. If you notice, starting right here, you can see what looks like a sine graph coming about here. And I could do the same thing with a sine graph. I could write it as a cosine. So they are just shifts of one another. All right, but where do we consider the cosine to be positive and negative? So you could think about that with a circle here at the center, thinking about cosine as being our x values here. These are going to be positive. If I go over here, these are going to be negative. Down here, these are still going to be to the left here, negative. And then right here, I'm going to begin to be positive again. So another way to say that, of course, is that I have my positive angles from 0 to 90 degrees. I'm going to include that because it is positive there. And then again from 270 to 360. And of course the negatives are everywhere that's not. The negatives would be anywhere from 90 degrees to 270. Again, your calculator knows that and it will show that as well. In general, we are going to think of our x values. When we're looking for an x value of something, we're going to think cosine. And when we're thinking of our y values of something, we're going to think of that as a sine because of what we just went through. When we were looking for something horizontal, we used cosine. When we were looking for something vertical, we used sine. So that actually should fit along with your whole SOHCAHTOA thing that you have been looking at. If I have a triangle anywhere, let's say that I have a triangle here, and I'm trying to find this y value, this height here, and let's say I know that angle, and of course I know the hypotenuse. Well, I'll just call it 20 because that's what we've been looking at. Well, then of course I'm going to use sine to find that. Opposite over hypotenuse. If I'm looking for this value, this x value here, I'm going to use cosine because I have adjacent over hypotenuse. So that's how that's going to work. Now, if I'm not in the first quadrant, I just want to draw this picture so you can keep this in mind as you start your Khan Academy work. These are what your triangle should look like in each of the quadrants. So remember, we always talk about an angle as being formed from this positive x-axis up and over. If I get into this larger or very, very large angles here, I can always use what we call a reference triangle and think about really just these angles here, 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 here. And that will help me in doing my work to find out things about heights or horizontal distances and things like that. If I can just draw this picture in this quadrant, find this value, or draw this picture in this quadrant and find this value, I'm still finding those y values and those x values. All right, I know that was a lot, again, I say, but please do the Khan Academy work and check back in later on the check-in. I would, again, try to do it on your own first and then watch the video to check in on it. Please let me know if you have any questions on this, or as you work through the Khan Academy, I will be happy to answer all of your questions. Please let me know. All right, I miss you guys so much. I'll see you later. Bye.